So hi everyone. So today we have Taro here giving us a talk on blockchain and address poisoning. So Taro is I think fifth year PhD student at CMU, advised by Professor Nicholas Christine, and he works at Scilab. He investigates emerging computer security threats and harms in the financial system, and he is a recipient of the Nakajima Foundation Fellowship for his doctoral studies. Taro, the stage is yours.
Thank you so much for having me today, and I'm excited to be back here. And some of you might remember that I gave a talk last year about blockchain amplification attack, which is one of my favorite projects, and it was a pleasure to work with Lee in this room. But I also really like this project as well, so I'm very excited to talk about this as well. And this is a joint work with Mark and Kyle and Nicholas, my advisor, and the paper was published at this year's Usenet Security. And to begin with, I'd like to ask you maybe two questions, if you don't mind. And so how many of you have used blockchain wallets such as MetaMask, Trust Wallet, Coinbase, and they do not really include the blockchain exchanges, buying cryptocurrencies from blockchain exchanges?
Oh, I raised my hand.
It's actually smaller.
Me too. Yeah, it's
okay,
smaller
thanks.
than what I thought.
Yeah, smaller than expected. And for those of you who use blockchain wallets, how many of you have seen blockchain address poisoning in your wallet?
I could say I
so the reason
yeah, I couldn't pay much attention, but I think I see the phishing transactions all the time, like small or
yes.
invalid tokens or just small amounts from random guy.
Mm-hmm. Yes. So the reason I asked is that address poisoning is one of the largest and mostly widely targeted attacks on chain. So, okay. So let's start the presentation. And to begin with, I like to start with some hypothetical interactions that I came up with my co-authors. So let's say I want to send $1,000 to pay my rent to my co-author Mark. And obviously he asked me to send it to his Ethereum wallet, which is a 40-digit hexadecimal string. But I didn't want to make any mistakes. So for testing, I sent him 10 USDT and he confirmed. So I sent him the rest of my money. However, he told me that he hadn't received his money yet. So I double checked my transactions and I realized that the recipient address I specified was slightly different from the original address that Mark told me. So what exactly happened behind the scene? So I, as a victim, sent 10 USDT to Mark's address, which is my intended address. And after this transfer, Mark's address shows up in my wallet transaction history so that I can copy and paste it next time. Very convenient. However, the attacker, Kyle, was watching this transfer and decided to generate a very similar looking address to Mark's. And because blockchain wallet addresses are derived from their secret keys, if he randomly brute forces secret keys, he'll eventually get the address that matches the first and last few characters to Mark's. And we call it a lookalike address. And if he uses this address to send a small amount to my wallet, his address also shows up in my wallet history. And because those two addresses look alike to each other, and if I do not check the address carefully and only look at the beginning and the end of the address, I might mistakenly choose the attacker's address instead of the intended recipient to send the rest of my money. And as we all know, blockchain transactions are not reversible, so my money is gone with one mistake. And even worse, we found that there are actually 3 ways to poison the victim's account. The first case is a tiny transfer. This is what I just described. So the attacker sends a small amount from the lookalike address to the victim. And the second case is a zero-value transfer. Here, the attacker uses a function called transfer from, where he can specify the sender and recipient from the arbitrary address. And usually you need a permission from the sender because you are using money from the sender. But if the value is 0, there's a quirk in the smart contract that you can actually launch a transfer from the sender to the recipient without any permission. So in this case, the attacker can launch a poisoning transfer from the victim to the lookalike address. And this is even more confusing because the direction of the attack is exactly the same from the original transfer.
So before, so I have just
Yes.
Some questions, right? So now you said the whole thing is possible because the victim only or the wallet UI at the victim's end is going to check only some positions of the address, right? So
Exactly.
my first question is, why is the wallet UI only doing this? I mean, why can't it check the entire address? Then the whole thing is not a problem anymore, right?
Mm-hmm. I think it's they are prioritizing the usability because the wallet address is 40-digit hexadecimal string. So if they display everything, it looks a little bit too long for them. So they just abbreviated in the middle. So that caused the issue. Also,
But like that should, I mean, so are you saying there is a human intervention? So the victim is actually doing a human input before the transfer, or everything is automated?
Human input.
Okay, so yes.
Sorry,
Go ahead.
Erwin, go ahead.
No, go ahead. I'm trying to understand this whole setup. Yeah.
Yeah. So the setup is, so basically the victim see a history of transaction. It could be receiving, it could be sending. And if you don't pay attention, if you see 2 similar address, you might just randomly click on the wrong one, which result in lose of found.
So this is when you say pick, these are like done by the actual human, and that's why there is a problem. I see.
Yes.
Okay.
Yes, exactly. Yes.
Exactly.
So it's not computer, there's an agent behind it. It's just human.
Okay.
Exactly.
I get it. Okay.
Sorry, I got a related question. Because you mentioned,
of course,
maybe the attacker can perform some local computation to generate a Bitcoin address, which is similar to the victim's one. My question is, how much computation does the adversary need to perform to generate a similar looking address?
I'll get back to the point later in this presentation.
Okay, good.
Thank you so much for the clarification. And to add that to the point, I have to emphasize that the wallets are not the only places that the victim makes mistakes. Sometimes they go to the web chain scanner and look at the transaction histories, and they only look at the beginning and the end of the address.
Okay.
All right. So, and the third case is a counterfeit token transfer. Here, the attacker creates a very similar token to the original one. And because the attacker controls the contract of that token, he can generate tokens out of thin air and send from the victim to the lookalike address. But in this case, the attacker can match the value transferred to the original one here, so that it looks even more convincing as well. So is this clear to everyone so far?
Yep. So, but I have a quick one on the zero value. So, is that indistinguishable from any legitimate transfer, like except from the fact that it's zero value?
Exactly. Yes.
So let's say the victim somehow sent a zero value transfer to make sure the address is correct in the first place. Then these two are indistinguishable, like basically impossible to figure out who is which one is how do I put this? Authenticated.
So usually
by
we look at the
on the right
order.
person.
Yes, usually we look at the order of the transaction because I'm sending it to the real actual money, like 10 USDT, to my intended recipient. We can know that this person is legitimate, and if the zero value is going to the address that is improbably similar to the original one, we assume that they are malicious.
Right. But kind of okay. So what if the initial $10 is just $0? It's also possible, right? And if that happens, it's impossible to kind of to tell which one is kind of the true
Yes.
intention later if they are kind of immediate.
Yes, that would be a little bit trickier case. But in practice, I didn't see much benign zero value transfers. That happens. Yes, that does happen in practice, but not much. So in that case, we ignore those cases. So we miss those attacks. But that's good. A really good point. All right. So our goal here is to go ahead.
Sorry, just one more question. I think on this slide, I guess the attacker is gonna send 990 USDT, right, to the victim, not 10, in order to trick. In order to oh no, sorry, I misunderstood. Yeah, it's correct actually. Yeah. So the original transfer is 10 USDT, right, to the friend. And
exactly. So the attacker doesn't know the amount of the next transfer. Yeah. Thank you. So our goal is to.
Sorry about that. A quick one on this slide as well. You said generate tokens out of thin air. Is this within the same transaction, or is there is another like you need to kind of mint this token in another one, or it can just be in the same transaction? The USDT.
That's a great question. Yes, that's a great question. There are a few ways to do this, but typically attackers just distribute them in other transactions, and those are not the transfer event, so that doesn't show up in the victim's history, but they distribute it in advance.
Right. Thank you.
Taro,
yes,
I'm wondering if those attacks are more targeted attacks, or if they can be launched kind of at a larger scale, because I can understand the attack could work well if there is a target wallet and you monitor the transactions and trying to mirror, through the phishing attack, something similar with similar looking with the targeted address, and also probably timestamps and so on that you can try to make them as similar as possible. But based on your analysis, by looking into the existing victims and attacks, are they more targeted, or if there are even smarter algorithms to launch such an attack at a larger scale? For example, based on the user transaction patterns behavior, whether they have frequent transactions, each time they pay 0.0001 unit of token, followed by a big transfer, which is something that a lot of people do. Or, you see this really as being, some users being really targeted and they are being monitored specifically.
Yes, actually, I'll get back to the point later in this presentation. I will talk about attackers' strategies, and we see some sort of sophistication as well.
Okay, all right.
Okay, so our goal is to identify those 3 types of poisoning transfers from the attacker, as well as to capture the payoff transfers sent to the victim to sent to the attacker to quantify the overall losses. Okay, so we use some heuristics to identify those transfers, and I'm going to give you a very high-level idea of what our detector looks like. First, for each block, we collect a set of accounts that transfer assets, and we call it a potential victim. And second, we collect all token transfers associated with each potential victim. And in this case, we only focus on the next 100 blocks from the original transfer to make the scanning process efficient. And this is based on the assumption that the attack happens right after the original transfer to make it effective. And third, we calculate the address similarity with the original recipient. And the distance metrics we use is simply the number of consecutive match digits until the other characters show up. So in this case, it matches the first 6 characters and the last 4 characters. And we only consider it to be lookalike if the score is more than 3 and 4 to avoid natural collisions. And finally, we categorize those transfers into 5 different categories based on the set of senders and receivers and the type of tokens and value transferred. And to make sure our detector is highly accurate, we performed a series of validations. One of them is to use external validation data set to identify a lookalike address from the set of benign addresses. And we achieved 100% precision and 97% recall. And we also looked at the largest transfers manually to make sure that they are actually successful attacks. And also we did some sensitivity analysis to make sure that model parameters are robust. For example, we are looking at changing the window size for the second part, the second process, and as well. Okay, so we run this detector on Ethereum and Binance Smart Chain for the last 2 years after the fact, and we identified 270 million attack transfers, over 70 million victims, and more than 6,000 cases contributed to $84 million losses, which makes address poisoning one of the largest and widely targeted attacks on chain. And to give you a sense of how active the attackers are, on the most active day on BSC, we observed 35 attacks every second, which means that the resources wasted on poisoning transfers are non-negligible at all. And another interesting thing that we found is that we observed many more attacks on BSC. And it is probably because transaction fees are 100 times cheaper than Ethereum. But we actually observed the change in this trend a couple of weeks ago, but I'll get back to the point. And in terms of losses, it is much higher on Ethereum because the average transfer size is significantly larger. So this means that the blockchain with smaller transaction fees, with many more economic activities, is the most vulnerable to this kind of attack. And finally, because wallet addresses are compatible between those 2 chains, we observed that 70,000 lookalike addresses are used between those 2 chains. And this means that the attack is easily generalizable and scalable, at least across different EVM chains. Okay, at this point, our question became, who is actually conducting this attack? So we started merging poisoning transfers to form attack groups. And here we are not only looking at the lookalike addresses that are used to deceive victims, but also any kind of addresses that support poisoning transfers, such as counterfeit token contracts. And we are merging 2 poisoning transfers in the following way. The first case is when they are launched in the same transaction. And oftentimes, the attackers bundle many transfers in one transaction to save transaction fees. So if they are in the same transaction, we consider that they belong to the same guy. And the second case is when they use the same address to pay transaction fees. And this is simply assuming that the attackers do not share private keys. And the third case is when they use the same lookalike addresses. In the end, the attackers need to extract money from the lookalike addresses, so there's no economic incentives to specify other people's lookalike addresses. So we ran this clustering for the first year of our measurement, and the results looked pretty promising. So I'm only showing the top 8 groups based on the number of lookalike addresses each has. And they are distinct over time and show very different characteristics. However, once we extend our measurement for the next 2 months, we started to observe that those groups started to merge to form one gigantic group. And I couldn't figure out the reason for a while because the clustering algorithm is very straightforward. However, eventually I came to realize that those groups are actually merged by a few accounts called copying bots. And those are accounts that unthinkingly copy other people's transactions from the mempool for the sake of front running or any other kind of MEV activities. And indeed, those attack groups are indeed those accounts copy transactions from 2 different attack groups, which violates the assumption we had about not specifying other people's lookalike addresses. So getting rid of those bots without removing many poisoning transfers is actually very tricky. But after trying a few methods, we came to realize that looking at the ratio of transactions that are used for poisoning transfers is actually pretty effective. For instance, copying bots copy all sorts of transactions from the mempool. So only few of them are poisoning transfers, but the attackers use the account exclusively for the poisoning transfers. So it is pretty easy to distinguish those accounts by looking at the history of transactions. Okay, so after removing those bots, we established 49 groups in total, and I assigned group IDs based on the number of lookalike addresses. And I want you to keep that in mind because I'm going to use that throughout this presentation. And in this table, we have the number of lookalike addresses, poisoning transfers, and counterfeit token addresses. And for this one in particular, we extracted the bytecode of those contracts, and I'm showing the unique number of source bytecode in the parentheses. And first interesting that we found is that the attack is fairly large scale. The top three groups have more than 1 million lookalike addresses and conducted more than 1 million poisoning transfers. And the second thing is the group 2 uses the same contract code for 1,500 times. And when we are clustering those entities, we didn't use any information from the contracts. So this actually corroborates our clustering results as well. And finally, we found that attack strategies differ group by group. And some groups even don't use the counterfeit token transfers, but they only focus on zero-value transfer, which again, this heterogeneity supports our clustering results as well. So based on these results, we are interested in inferring attackers' strategies and capabilities. And this is going to answer one of the questions we had in the beginning. But the first thing we wanted to look at is that which population our attackers are actually targeting. So to answer this question, we prepare a set of victims for each attack group and retrieved their balance before the first attack. So this figure is the cumulative distribution for the victims' balance for the top 7 groups, plus the baseline, which is randomly sampled USDT users. And the more right you go, the richer they are targeting. For instance, the median balance for the baseline group is about 400, whereas the group, it is over 70,000 for group 605. So this is a clear evidence that the attackers are targeting richer accounts to extract more money. And we also looked at the level of activities and also the size of transfers as well. And we picked 100,000 of the most active users and the accounts with the largest transfers, and again, a random baseline. And this figure also has the cumulative distribution for the number of attacks each account received. And the more right you go, the more attacks they get. And again, it is pretty obvious that the attackers are targeting active accounts or large transfers more than the baseline. However, I want to emphasize here that even for regular users, more than a quarter of users receive this kind of attack at least once. So if you are using, US Tether, the chance of getting the attack is about 25%, regardless of your economic activities. So this is a very prevalent attack on chain. You go ahead. Yeah.
Oh, sorry, just a stupid question. What is the baseline again?
I just randomly sampled users who have transferred USDT in the last 2 years.
Okay, I see. Thank you.
Thanks for the clarification. And okay, so the next question we had is this attack profitable? And the short answer is yes. But we are also interested in who is actually profiting the most, what the market looks like. And in this figure, x-axis is the total cost, which is the sum of transaction fees plus the transferred value sent to the victims in the case of tiny transfers. And y-axis is the total revenue, which is simply the amount of payout transfers in USD. And each data point here represents each attack group, and the number is the ranking of the group based on the number of lookalike addresses they have. And group 1, for example, spend a few million US dollars just for poisoning transfers. So again, the attack is fairly large scale. And second, the large groups are very profitable. They experienced about 10 to 20 times the return on the investment, whereas smaller groups experience losses. And the part of the reason is that the variance of this payout transfer is quite high. So if you're lucky, you might get millions of dollars at once, but most of the cases you get up to 100 US dollars. So large groups actually manage to diversify the risks by having many payoff transfers. And indeed, we found another advantage of operating this attack at large scale. So when we are looking at successful cases, 79% of the time, multiple attack groups are competing against the same victim. So in this case, my third co-author, Kyle and Nicholas, are competing each other to exploit Taro. And if the Taro sends back money accidentally to Nicholas, we record win for Nicholas. And this figure shows the winning ratio for the attack group in the y-axis over the groups in x-axis. So for instance, group 1 wins against group 2 60% of the time, and group 2 wins against group 8 92% of the time. So we have a darker blue here. And this figure tells us that the top groups are fairly competitive, meaning that the winning ratio stays about 50% of the time, whereas they dominantly win against smaller groups. And the reason behind this is that the large groups have more resources to conduct attack early or generate more similar looking addresses. And we actually have another experiment to verify that claim. So please look at our paper later. But another goal for the attacker is to generate as similar address as possible to the intended one. So this also answers one of the questions we had in the beginning, but we are interested in looking at the similarity score distribution of those lookalike addresses. And in this figure, we have the number of match digits, which is the sum of the similarity score. So this is a total number of match digits in the beginning and the end. And y-axis is the number of lookalike addresses generated by each group. And it is pretty clear that group one managed to generate much more similar looking addresses than other groups. And we are interested in where the difference comes from. So we first looked at, we first mathematically approximate how many attempts you actually need to generate such an address. And after applying a geometric distribution and also Taylor approximation, we get the number, we approximate a number to the 16 to the number of match digits divided by the number of target addresses. So for instance, if we want to match 7 digits in total, let's say 3 in the beginning and 4 in the end, and okay to be matched with any of the 100 accounts you are targeting, you need 2.7 million attack attempts. And then next, we empirically estimate how many addresses you need to generate such an address. How many addresses you can generate per second maximum, so that we can approximate how long it takes to generate such an address. So we started with the off-the-shelf implementation using Python and Web3 libraries, and we achieved about 1,000 to 10,000 addresses per second. And then we tried different kinds of libraries and also programming languages and adding multiple CPUs, and the number goes up to 100,000 addresses per second. And this is the maximum you can get by using CPUs. However, if you add GPU, the attackers can generate up to 1 billion addresses per second, which is simply frightening. But if you remember from the figure from the previous slide, the group one managed to generate 6 more digits than other groups, which requires about 10 times the computational power the other groups have. So we conclude that group one must have used GPUs or any kind of specialized machines, because generating or matching 20 digits by CPU takes astronomical number of years. Okay, is there any questions so far?
Yes, for the previous slide, why the shape of group one looks a bit weird? It drops first, right? And then increases again, the red. What's the reason for that?
So my guess is that they are using both. They are using both CPUs and GPUs.
Or
And
maybe they just. Sorry, Taro, you go
sorry,
first.
go ahead. And so this is just a speculation, but at the time, most of the wallet providers are showing only 3 and 4 digits. So the attackers only need to mask the 3 and 4 digits, but also the scanning providers mask 6 and 7 digits. So maybe the attackers had 2 ways of generating the lookalike addresses. This is purely speculation, by the way. Yeah.
And yeah, sorry, one of my speculation is they might just avoid competition for lower bits. if they quantify their score in that way, that could be. But like, it seems, I don't know,
because it is
matching more digits needs more computational power, means it's more expensive. So it doesn't make sense just to avoid competition.
I mean, the other question I have is, yeah, go ahead, Taro.
Generating such a similar looking address by GPU is very expensive as well.
Okay, so the other thing I was thinking is, you know, like when doing, you know, password, right? Like you have this rainbow table, right, where you can do some lookups. I guess for here, if you only want to match a few digits, right, then it's feasible to have a giant table with all the private key and public key pairs pre-computed, right? And unless you want to match more digits, then you probably need to do some computation on the fly. Because you don't have like infinite storage space. But I mean, if it's only, I don't know, 8 digits, it should be fairly easy to just store in a hard drive, right? Is that true? Or did I misunderstood something?
I assume that yes, it is pretty easy to pre-compute those lookalike addresses, especially if you want to launch the attack right after the original one. But off the top of my head, I do not know it is effective to calculate everything in advance because the number of addresses you're targeting is very large.
Right, because I was thinking from the shape, it looks like when it's less than, let's say, 12 digits, they somehow follow some other methodology, right, than using the GPU. And if I'm wearing the hat of the attacker, then I would store whatever I found, right, on a disk, and then just like do a lookup instead of recomputing everything every time, right? Which is very costly for me. Because sometimes I also generate, you know, like addresses myself. I know it takes a long time to generate, so I want to have my address prefix with like D file or whatever, right? So I do generate funding addresses myself.
Right.
But yeah.
Yeah. Thanks for the insightful feedback. Yes, definitely optimization. The attacker needs some sort of optimization as well. Okay, so how can we mitigate this issue? So we propose mitigation at the different layers, and the first one is at the protocol level, and we can always use a human readable wallet addresses such as Ethereum naming system. However, this introduces another security issues such as typo scoring. And also we can make it more difficult to generate such similar looking addresses. And so the idea is to add more latency for address generation using cache heavy function or verifiable delay functions. At the contract level, we can completely remove zero value transfers. But the community found out that people actually sometimes use zero value transfer for testing. So it actually breaks the existing code on chain. And at the wallet level, the providers always should improve the UI as well, so they can increase the number of digits they display, as someone mentioned in the beginning. And we can also they can also give a warning based on the heuristic similar to what we had for the detection system. But in the end, this comes to the user's mistake. So it is always a good practice to whitelist your intended address. So if you are using non-custodial wallet blockchain wallets, I recommend to do so. But as a researcher, it is always important to warn users of the severity of this attack. So as a follow-up of this paper, we developed a real-time detection system, toxin tagger, that can actually keep up with the speed of the chains. So originally, we designed our detector on the historical data, but we wanted to do it on real time to warn users. But the challenge we had here is that every block comes less than 1 second on BSC, so which requires a lot of engineering. But my second author, Mark, did a great job implementing this system. So we now have the website. So actually, I want to go through this website with you. So if you have phone, please scan this QR code or type this URL. And
Right, just a irrelevant one. Is the T-T
Sure.
trying to show a crying face or
yes, crying face.
okay.
Do you have any other questions before going to the website? Cool. So maybe you're looking at the website right now, but we broadcast whenever someone makes a mistake. So this happened a few days ago, but someone lost 160,000 US dollars. And in the last couple of days, there are 2 more cases with more than 100,000 US dollar losses. So this is a real threat. And if you click the tab, you can actually see the detail of this attack. For instance, you can see exactly when the victim initiates the first transfer, and then 4 blocks after, the attackers perform the counterfeit token transfers, and an hour later, it's actually less than an hour, the victim makes mistakes to send 160,000 US dollars to the attacker's address. Okay, and we actually have social media account that broadcasts these results live. So if you like the system, I would appreciate if you could follow the account. But as a researcher, I think it's really important to keep working on the problem even after we submit the paper. And indeed, we our continuous monitoring captured a very interesting trend in a few weeks ago. And this figure shows the daily number of poisoning transfers on Ethereum. And we have the number of poisoning transfers and also 3 different kinds of poisoning transfers and the intendeders, which is a benign transfers, the intended transfers. And on this day in particular, we found more than 2.5 million attack attempts, and which is about 15% of the last 2 years of our measurements. So we initially thought this is a bug in the system, but it turns out the transaction fees on Ethereum is actually significantly smaller these days. So some attackers scale up their operation. And because it used to be the case that 2.5 million attacks is about 2.5 million US dollars, costs 2.5 million US dollars, but now the cost is about 1% compared to the last year. So we find it really interesting. And in terms of BSC, we keep capturing about 1 to 3 million attacks per day. So the attackers are still very active these days. Okay, so in this paper, we identified 270 million attack attempts and 80 million for US dollar losses, which makes address poisoning again the largest and widely targeted attacks on chain. And I think it is really cool that we can capture all the failed attacks. And this is not really possible from the traditional cybercrime research because all the information gets lost in the middle. And we also show that there exists an economy of scale. And because the attackers keep using the same accounts over and over, we were able to cluster them based on their on-chain activities, and we show that they are very profitable and dominating the market. And I also find it really interesting that we were able to infer attackers' hardware capability just based on the simulation and measurements as well. And we disclosed our finding to the relevant service providers and made the dataset publicly available. And I couldn't talk about many experiments in this paper, so if you are interested, please read the paper as well. Thanks for listening.